Is it okay like this? Can you hear me? Okay. So, do you want to know the answers to the homework of yesterday? No? Yeah? So the exercise, the first one was about really the simplest lens we're talking about all the time, which is the isothermal lens, with a potential that by now you should be able to say in your sleep, Einstein radius times angle. And what we showed yesterday when we about axisymmetric lenses was that you have nice formulae for the convergence and for the tangential shear. And that's really all you need to know to the magnification. In the end, the magnification is the determinant of this matrix which we saw before, minus kappa minus gamma squared. So this exercise is really nothing else than taking your potential, calculating kappa and gamma, putting it in the magnification matrix. Right? And I'm not going to do the derivation here. In the end, you end up with 1 minus theta e over theta. And so this is the compression, this is the conversion from the image plane to the source plane, and so the magnification is actually 1 over this determinant, so it's 1 over 1 minus kappa squared minus gamma squared. And so that shows that when the Einstein ring, when you have an image on the Einstein ring, then the magnification is infinite, right? This m goes to 0, 1 minus 1. So 1 over that gives you it's the critical curve. There you have infinite magnification. The images are stretched from a point into a full ring. And when you go to very large angles, then this becomes a very small term, and you just have 1 minus theta e over theta to the minus 1 is approximately 1. So the further you get from the lens, the closer the magnification becomes to 1. In other words, the lens becomes weaker and weaker and weaker. Is that okay? So it's really applying what we know of symmetric lenses, given the potential, into the magnification matrix. Second one is a bit more complicated. I don't have the wiper again. I need someone to clean the board. So in the second case, we have a lens at a certain point, and we know that that lens produces 2 images of a quasar, image 1 and image 2, at position theta 1 and theta 2. And I've told you that this angle is 1 arcsecond, and this angle is half an arcsecond. So what this shows you immediately is that this is not a symmetric situation. Right? This is not a case where the source is sitting right behind the lens, because then we would get a ring. The source is somewhere here, it's somewhere offset, so that you just get 2 images. And what the point of this question is that once you know the potential, you know it's a singular isothermal sphere, so you know, once again, that's the potential. So the deflection angle is the gradient of psi, which is theta e. It's just a constant for the singular isothermal sphere. And so the lensing equation tells us that the source position is equal to the image position minus the deflection angle. And now we don't know where this image position, where the source position is, but we do know that these 2 images come from the same source. And so that means we can put the 2 images into this lens equation, and we can get beta 1 equal to 1 arcsecond minus alpha. So that's this one here. And beta 2 is equal to minus a half arc second, this position here, plus alpha, bending in the other direction. And in this case, alpha is normally a function of theta, but in this case, alpha is always a constant because it's a singular isothermal lens. And now because we know that these images come from the same source, we know that they have the same beta, they have the same source position. And so therefore it's very easy to work out what the deflection angle is. Alpha is, in the case of a singular isothermal sphere, the separation of the two images is always equal to twice the Einstein radius. Great. It's a different one. So what we've done now is we've started from a lens where we know the kind of lens, but we don't know this theta e. We didn't know this, and we've used the images to solve for what theta e is. Sorry, theta e. I meant theta e is equal to 0.75 arc seconds. And so once you know now the lens, we now have the lens potential exactly. Then you can do all the kind of questions that I'm asking you about what the mass distribution is. Right. So for example, the mass within a radius of theta, the enclosed mass, we know that alpha is equal to the mean surface mass density divided by theta, sorry, times theta. Right? Let me just check. Yes. And so therefore, at a radius of 0.75, we know that the mean surface mass density inside is equal to alpha over theta. Alpha is the deflection angle, which is 0.75 arc second divided by 0.75. So in this case, it's exactly equal to 1. Right? And this is the old result. I'm asking you exactly at the Einstein radius, the average surface density within the Einstein radius is always equal to 1. And so to turn this into a mass, turn the kappa into surface density, which is obtained by multiplying by the critical surface density. You go back to the first lesson. And once you have the surface density and you have the area of your circle on the sky, then you can work out what this radius is, and if you have the radius. So the mass is pi times the surface mass, the mean surface mass times the radius squared. Mean surface mass we got from our mean kappa, and the radius you get from multiplying the distance to the source with the size of this ring. And I've given you the redshift. So once you have the redshift, then you can work out this radius. Z gives you the distance to the deflector, which is 0.1 times c over the Hubble constant. C. So the redshift is in a fraction of the speed of light. So redshift of 0.1 means 0.1 of the speed of light, recession velocity, divided by the Hubble constant. And then you multiply by the angle in radians. just gone to sleep. So that tells you the first part, right? Is it clear more or less what the strategy of this solution is? So first you use the image separation to calibrate the strength of the lens. Once you have the strength of the lens, you can work out what the mass is within any area you like from using the lensing potential and the relation to the mean surface density. Okay, now part B. Any idea for part B? How does the surface density go in a singular isothermal lens? The second derivative of theta is 0, and the first derivative here is just 1, so 1 over theta, all multiplied by theta e. And so the singular isothermal lens is actually a lens where the surface mass density goes like 1 over the distance from the lens. So part B is the same as part A. So once you've solved A, you've also solved B. The same thing. Singular isothermal sphere has a surface density that goes like 1 over r. Now for part C, we have a different surface density profile. For part C, we know that kappa scales like theta to the minus 3/2. So I'm going to look. If we try a potential that goes like some power, then here you see that you end up with a power that's too lower by the time you calculate kappa, because you take a second derivative. So and so from this you can read off that when kappa goes like theta to the minus 3/2, psi has to go like theta to the plus 1. You raise it by 2 powers. And then once you have done this, you can do exactly the same as we have before. So you don't know the amplitude of the lens, so you make that a variable. The deflection angle is the gradient, so that's A over 2, square root of theta. And you solve the lens equation again. You say again that beta 1 is equal to theta 1 minus alpha of theta 1 is equal to theta 2 minus alpha of theta 2. And so again, saying that these are two images of the same source at position beta. And so the one image is at 1. The deflection angle at 1 is A over 2. The second image is at minus 1/2. And the deflection angle at 1/2 is A over 2 square root of 1/2. And so this is the information you need to calculate A. And then once you have A, you do exactly the same as you did before. You put it in here you can use again the fact that alpha is the mean surface mass density times the angle. This you know from the potential, so that tells you the surface mass density within this radius of 0.75 arc seconds, and you're back in business. And what you find here when you do this is that the mean surface mass density within is, I forget the number, it's a little bit different. It's 0.96. So here for the singular isothermal lens with images in exactly the same place, we found an average surface mass density of 1. Here we find a lower surface mass density. So with the same image position, but with less mass, we're able to do the same amount of lensing. Right? So the mass depends on the lensing model. But the strategy is exactly the same. Use the image positions to work out the strength of the lens, and then use the strength of the lens to work out the mass. And then D is exactly the same again, but now we have a point mass, so now we have a potential that goes like 1 over the angle, so not 1 over the square root of the angle, sorry, yeah, goes like 1 over theta. And so, no, log. That was the bending angle. Point mass has the logarithm of theta. And you can again go through exactly the same. And what you find here is that the surface mass density is even less. Something like 0.88. Right, you can see how you would solve the same case, right? It's exactly the same thing, but now you have a different, you will end up with a different relation because you get a different alpha of theta dependence. So what about the last part of this question? How could you tell the difference? Because all of these different cases are situations where we have exactly the same image positions for a quasar. We see a quasar, it's split by 1 arcsecond one way, half an arcsecond the other way, and I've given you 3 different lenses that can do exactly that give you exactly the same on the sky, as far as image positions go. So what extra information could you try to use to figure out which of these lens models is the correct one? Any ideas? Any ideas in Spanish? Yeah.
If we had a time delay between like 2 flashes, with that we could see maybe the difference. Like we could use the Fermat potential to see which one fits better. Yeah. Like to get a better restriction on the form of the lensing potential.
It's true, the time delays would be different in these 3 lenses, so if you could measure this, it would help. There's an even simpler way of trying to do this. It's related to what you did in question 1. Question 1 was about magnification. And you will find that these 2 images are not equally bright. One is brighter than this one, is going to be brighter than this one. And the ratio of brightnesses will be different for the different lensing models that we discussed. So if you work out the kappa and the gamma for each of these different lens models and work out the lensing magnification, you will find that it's not the same. And so the image positions are one important piece of information, but also the relative brightnesses of these images are another second important piece of information to try to distinguish between lens models. Okay? And then part 3 is very quick. Who can tell me the answer to? Who can tell me the answer to the 3rd question? as soon as you see it back on the screen. So we have a 5-image quasar. And this quasar has an eruption, so we get a flare. These flares travel along the different paths to the different images. These paths have different lengths. Which one is the shortest and which one is the longest? It goes first or last? First? Okay. Who agrees? Who disagrees? You think it's last? Okay, who thinks last? Who thinks first? Let's have a vote. It goes last. So if you think of this Fermat potential, right, this is the Fermat potential without the lens, and then the potential of the lens introduces a bump, and this is the arrival time. So the arrival time here is later than the arrival time elsewhere. And what about the other ones? If you remember, the Fermat potential ended up with some minima and some saddle points. Kind of difficult to draw here, but you had 2 minima and 2 saddle points, and then the maximum in the middle. So which are the ones that come last? Oh, that come first. The minima come first because that's where the arrival time is smallest. Yeah. So first you get the minima, then you get the saddles, and then you get the maxima. And so this can actually help to solve a lens model as well, because if you see such a variation, you can read off where the minima and where the saddle points are. So sometimes it's not clear from the configuration. This helps. Okay. That was it. So how was the quiz today? Too long? Okay, so the topic of today is microlensing. So today we're going to talk about a different case of lensing, which is microlensing. So not the strong lensing that we discussed yesterday, but microlensing, which is something that happens inside our own galaxy. And so for microlensing, the idea is that if you have us as observers looking at some star in our own Milky Way, then every once in a while, along this line of sight, there's going to be another star. And the star is going to be so well placed that it acts as a gravitational lens. Now, we worked out before that the critical density for lensing inside the Milky Way is extremely high. So lensing is a very weak process inside the Milky Way. So that means this alignment has to be incredibly good. So it's a very rare thing. But nonetheless, it means we have to look at lensing by point masses. And so we've seen this before. Lensing potential is logarithmic, so the bending angle goes like 1 over theta. And so the lens equation becomes very simple. And it's an equation you can solve directly, analytically. Right, it becomes a simple quadratic equation for theta, and the solutions depend on beta and on the Einstein radius. So we always have two images. And you'll see that there's always positive in one. So there's always a positive and a negative root. And when theta is very large, so the source is very far from the lens, you basically get up with one root very, very close to 0 and the other root very close to the source position. So I think I have some images of this on the next slide. So this is the kind of solutions that you get when you have point masses at lots of different positions with respect to the lens. You get these double images, again, split by the location of the Einstein radius. Now, the other thing we can work out is the magnification. And for a point lens, you can show very easily what the surface density is. Surface density is 0, except in the middle. Right? All the mass is in the center. There's no mass outside the center. And you can show from the potential that the tangential shear is equal to theta e over theta squared. And so therefore the magnification kappa is equal to 0. So it's like this. So this is the inverse magnification, and so when we take 1 over this, this is what we get. So as before, at large angles, the magnification goes to 1. Goes to 1. And when you're at the Einstein radius, the magnification goes to infinity. Right? Same thing as with the singular isothermal sphere, but just a slightly different functional form. Now, what we can do is we can put the two solutions for the images in there. And we can work out what the magnification is as a function of beta, not as a function of theta. So in other words, we can work out how much an image is magnified when the source is at a certain position. And this is a messy calculation which I will not go through, but I'll just show you the answer. This is the magnification of the plus image and of the minus image, where I've now substituted into this formula the value for the image position. And what you can see from this is that one of them is positive and one of them is negative. Again, if you stare at this formula long enough, it becomes obvious. So one of the images is inverted, and the other image is not. Okay. Now, why am I doing this? Because in microlensing, the image separation is really, really small. So all of this happens within a milliarc second. Typically. So if this is the case where you have a star inside our own galaxy, let's say 10 kiloparsecs away, and another star somewhere along the site, then typical numbers will tell you that this Einstein radius is incredibly small. And a milliarc second is basically much too small for us to be able to see with a telescope. You cannot take a picture that sharp. And so what instead what you have to do, the only thing you can work out is that this star in the background is magnified. You see more light coming from the star than you would otherwise if the lens were not here, because we have this kind of focusing effect. So it's like a little magnifying glass that we have on the star, and we can, there's more light coming in through the magnifying glass, but we cannot actually see that the light is split into two separate images. So all we're interested in is the total magnification, the total flux of these two images put together. And so what we want is the total magnification remembering that one of them is negative, but the focus doesn't care whether the image is upside down or not, all the light adds up. And so this is going to give you, again, let me make sure I get this right. There. Yep. So this is really the central formula of microlensing by stars in the galaxy. This tells you if you have a star right behind another source and it's within a certain fraction of the Einstein radius, then this is how much that star will be brightened. And so, for example, when you're at an angle equal to the Einstein radius, then you get a magnification of about 1.34, which is kind of a magic number in microlensing, because it sets the threshold. So if you have a lens on the sky with its little Einstein circle of maybe 1 milliarc second in size, if you have a background star that is right on this Einstein circle, then you will get more light from that star than you normally would by a factor of 1.34. And so the way to think of microlensing is that if you think of the distant stars as basically fixed, and you have stars in between which are moving slowly, then as these stars move in front of one of these background stars, the background star will flare and go back down. It will give you a kind of temporary brightening. And that's what you can see here in this graph. Here is the star as it appears without the lensing, and these are the images that are actually produced by the microlens sitting here right in the middle. And so we simply see all the light that fit in a much larger area than this, so we cannot see these separate images, but we can see the total flux. And so what you can see is when the star is close to the middle, these images are quite a bit larger than they were originally, and so you're gathering more light from this star.
Good, but I don't understand why you have a single maximum instead of two maxima, since the maximum magnification is obtained when beta is equal to theta e, so you should have two crosses of the critical curve.
This is not the maximum.
Ah, this is not the maximum.
No, the maximum can be, it goes like 1 over beta. So
okay.
If you go really close to the center, you get a really high magnification.
Okay.
In principle, you can go infinite. It's just that this kind of sets this Einstein disk sets the scale, and at that scale, this is the magnification that you get. And this is also a nice number because it's something, it's not very large or very small, it's actually something you can imagine observing or detecting. And this is the threshold that traditionally microlensing projects have set to find events.
So the maximum magnification, how to say it? Yes, as you said, this is the threshold. So you have to be able to detect 34% of increase in brightness of the star.
If you detect that, then you know that the background star is sitting behind the Einstein disk of the lens. Of course, if you can detect 10%, then you're sure that's also fine. Then you know it's within maybe 2 2 times the Einstein disk, but this is just the number people work with. And so this is what you see on the sky, right? You see the flux as time goes on, beta changes, right? Here the source is far from the lens and outside the Einstein radius, so here beta is bigger than 1 or bigger than TTE. And then as you get closer and closer and closer, beta reaches a minimum, and then it goes away again. It's a perfectly symmetric thing. And so in time, depending on how close you get to the center of the lens, you get these various light curves with a single peak symmetrically going up and down. And in fact, I think I have some movies of this in the presentation here. Okay. Here's an example where the lens, you can see the lens in the middle. The lens is the point in the middle. The circle is the size of the Einstein radius, of the Einstein disk. And the source is a little pink blob that's peaking on the left, and it's going to track across horizontally as we start this movie. So this, and you will see the images in black and the source position in purple. This is the image in black, and you see very nicely the effect that we've talked about this whole week, that gravitational lenses push away images from their center because they make a detour to get to us. So this is the case where beta is about twice the Einstein disk. So you see there's a very small, if you look very carefully, you see the image gets very slightly larger, so there's slightly more light that we're catching, but this may be a time. And I'm not sure whether you can see it from here, but there's also very, very faint, very tiny second image that appears and disappears. Right? Point lenses always give you 2 images, but one of them is much, much bigger than the other. You're far from the lens. Okay, let's make it more interesting, and let's bring the source closer to the lens. So now the source is going to track inside the disk out to a distance of 0.7 times TTE. So think what's going to happen. So now you see the second image very clear in the middle. And so this is again extra light from this star that we wouldn't get if this lens was not here. So the image out here also gets larger, so that image also gives us more light, but in addition there's the second one. And so that's why we've had to add both of the solutions together to get the total amount of light that this lens is catching from the sky. Right? And so remember, this is all completely unobservable. This is all this motion is something we cannot see. It happens on scales of milliarcseconds, which we cannot detect. Now let's get even closer. This is an impact parameter of 0.3, so it's going to come about here. And now you'll see the same effects, but even stronger. You see very nicely the role of the Einstein ring as the critical curve. Right? Near the critical curve, the images get very distorted. And you see the role of the central point as the caustic. When you come close to the caustic with the source is when all the strong lensing effects occur. So this is actually strong lensing, but it's strong lensing on such a scale that we cannot see it. All we see is the total light. And let's go even closer. This one goes almost through the center. And then you see a very strong effect. Very, very short but very strong period when there's a lot of extra light coming from the... I'm excited too. And if you were to go exactly through the middle, you would have a moment when there's a perfect Einstein ring, which effectively gives you an infinite magnification. And so these again are examples of these light curves that you saw before. And so there's something very nice about these light curves. When you see, if you can measure the peak magnification, if you can figure out how much the star is brightened in the middle at the closest approach, that immediately tells you how close you came to the lens in terms of Einstein radii. Because the central peak brightness, the central magnification, you can solve here and you get beta over TTE directly. Okay. And so this principle is what people have to try to solve a problem in galactic astronomy. We know that the galaxy, we see the disk of the galaxy, there's a central bulge, but we also know there's a lot of extra mass, a lot of dark matter surrounding the disk of the galaxy. And we still don't know what this dark matter is. And one of the possibilities maybe is that it's some kind of dark star or collapsed objects or hydrogen clouds or whatever. Compact, massive things which are moving through the halo and actually containing a lot of mass and producing this extra gravity that we measure. Now, the macho, and those things are called machos. Macho stands for a massive astrophysic collapsed halo object. And this is to contrast it with WIMPs, which is the other candidate for dark matter, which is weakly interacting massive particles, which is a particle physics. So, machos and WIMPs, it worked very well. This is in the 90s when this was a big thing. Now, if the dark halo consisted of a lot of these massive objects, of these machos, then they would cause microlensing. And you can calculate how often this microlensing would take place. And it's a small probability, but it would actually happen. So later on we will calculate the probability of this happening, but it's about 1 in a million, let's say, at any one time. If the halo consisted of microlensing objects, not of small particles, but of microlensing objects, then you would get about 1 star in a million being microlensed at any one time. So 1 star in a million would be brighter than it should be by at least a factor of 1.34. Now that sounds very nice, but you go and find that 1 star in a million that's doing this. Right? So if you take a single picture of the sky, that certainly isn't going to help, because you don't know what the brightness of the stars are. You see, you don't know whether a star is unusually bright or whether it's always the brightness that it has. And so what you have to do is you have to monitor. Over time, measure the brightness of lots of stars and see if they're constant or if they're varying. And if they're varying, see if you find ones which vary in this very characteristic way, with a single symmetric peak going back down. And that's not easy because there's lots of stars that vary for lots of other reasons. You can have eclipses, you can have eruptions, you can have pulsations. And so actually when people did these experiments, they learned a lot about variable stars as well as about microlensing. They even discovered new classes of variable stars that hadn't been done before. Now, because this is such a rare thing, it's no good to simply measure a few thousand stars. You really have to measure millions and millions and millions of stars. And so the way people did this was they took parts of the sky where there are a lot of stars behind a lot of halo. And so the obvious place where you end up is the satellites of the Milky Way. So this is a cartoon of the galaxy, this is the central bulge, this is the disk, surrounded by this large dark matter halo. And we have these satellites called Large Magellanic Clouds, which in Holland we cannot see, and here you cannot see either because it's always cloudy at night. But nevertheless, they're very nicely visible. And there are a lot of stars in a small patch of the sky. So if you take a few pictures of just this part of the sky, you're immediately catching millions and millions of stars, which is what you want. And so these experiments, one was called the Macho experiment, one was called the Eros experiment. The Ogle experiment is actually still going on from a telescope on Las Campanas in Chile. What they do is they take pictures of these areas where there's lots of stars, night after night, hour after hour, and they measure the brightnesses of all the millions of stars that they find on these things. Automatically, of course. And then you build for all the stars these light curves, like I showed you here. And you look for the ones that have the single. So that's one thing you can do. You can try to figure out how often this occurs, and that tells you something about how many and how massive of these collapsed objects there are between us and the Large Magellanic Cloud, let's say. You can also do this experiment looking at nearby other galaxies. For example, I was involved in an experiment looking at the Andromeda galaxy, which we can see from Leiden, and maybe, I guess you can see from here too. But that's nevertheless, it's a northern hemisphere galaxy. So I'll talk a little bit more about these macho experiments in a second. But let me already advertise what will come in the second half, which is other applications of microlensing which are maybe more exciting, or at the moment are certainly more alive and more actively being researched. And one of the main ones is to use it to find exoplanets. Because what I showed you here was the lensing by a single point source. But it turns out to be very interesting what happens if you add a second, very much smaller point mass to the lens. Add a second point mass, you make a binary lens. It turns out that in some conditions, lensing can be extremely sensitive to even a very small extra perturbing mass. And so it's a way of finding planets that accompany the lens that's doing the microlensing. So I'll talk about how that works later on. And the third thing you could do, and I'm not going to talk about more here, is to use it as a kind of gravitational microscope, because if you look at a giant star, for example, it can be that the giant star is larger than the Einstein radius, and so you're only magnifying a small part of the surface of that star and not the whole star. And so as everything moves, you're kind of scanning a microscope across the surface of the star and learning something about basically resolving the size of a star very far away. Let's see. So let's work out how rare microlensing really is.
Koen, please, could you use another color for the marker?
White?
In this wavelength.
Like this?
Yes.
So how likely, or in fact how unlikely, is microlensing really to happen? So let's say that we define microlensing to be the situation where you have a lens on the sky somewhere with its little Einstein radius around it, and we're going to call something microlensing if there's a background star that's sitting behind this disk. So not nearby, but actually behind the Einstein ring, and that's what gives you a magnification bigger than this magic number of 1.34. So then what we have to work out is if you take a patch of sky and you take all the stars in that patch of sky, you draw the little Einstein circle around each of these stars, and the question is what fraction of the sky is covered by these circles. In other words, if I put background stars in random positions, most of them will fall outside, very few will fall behind one of these things. What's the area of these circles compared to the rest of the sky? Now for that we need to know how big the Einstein radius is. And we've worked this out in the first lesson, so I'm not going to repeat the calculation here. But I hope you agree that it's equal to this. So this is the size of the Einstein ring, not the angle, but the size of the ring around the lens, given the distances and given the mass of the lens. And notice that this depends on the distance. So if we have a particular star, so let's have a source star here, an observer here, so this distance is going to be the distance to the source. And we have our line of sight. And so at every position, at every dd, at every lens distance, we have an Einstein radius. And that Einstein radius is going to be different everywhere. And it turns out if you work out what this looks like, it actually looks like a kind of cigar shape. When dd is very small, the Einstein radius gets very small. When dds is very small, the Einstein radius gets very small. And the maximum is when the lens is exactly halfway between the source and the lens, the source and the observer. So this is the kind of dependence you get. And so you have to put lenses inside the cigar for the false microlenses. Any star that falls outside here, its Einstein radius is not in front of the star. So you can think of this as lots of different Einstein disks in here. And so the question is, what's the volume of this cigar? Or rather, how many stars are there in this cigar? Well, that's an integral we can work out along the line of sight. So if we go along L from here to the source, it's simply the area of the cigar times the depth. So it's pi RE squared times the number of stars that we have at each position. And the number density of stars is equal to the mass density, which will change as L as a function of position, divided by the mass of the star. So at the moment I'm assuming that all the stars have the same mass.
But what is this letter inside the density?
1 second.
This is L. L.
L is our coordinate along here. It's just the integration. L is the length, the position from here to there.
So is rho as a function of L?
Rho is a function of L.
Okay.
Okay? And now all we have to do is plug in our expression for the Einstein radius to do this integral. And over m. So I've kept the rho of L over m, and I've replaced RE squared by what's inside this square root here. I've replaced ddx here by dd by ds minus dd. dds. And to be able to work out this integral, you need to know what the density is as a function of distance along this line of sight. That's going to be different depending on the direction you look in the galaxy. But nonetheless, we can estimate roughly how big this number is. And you end up with something roughly like one other important thing. I'm going to use a different color for this. You see the mass drops out. The mass cancels. So you can actually do this with heavy stars or light stars. You get exactly the same amount of microlensing. It'll be different because the size of these disks will be different. But if you have the same amount of mass in massive stars, you will have a few big disks. Or if you have it in a lot of light stars, you will have a lot of small disks. But the total area is going to be the same. And that's because R squared goes like m. Right? So the area that you cover goes like m. So if you divide the same amount of mass over different stars, you end up with the same total area that you're covering. So in the end, it only ends up depending on the total amount of mass, not on the masses of the individual stars. So that's another nice thing about microlensing, that it measures the total amount of clumpy mass in one go. In a fairly model-independent manner, although when you go to actually doing the experiment, all these nasty things begin to come back. But okay, we were estimating this integral, 4 pi g over c squared, the mass disappears, and then we have basically a length squared, so it's something like the distance to the source squared times sort of average value of the density along your line of sight. You can put in some typical numbers. In the galactic halo, you have something like 0.01 solar masses per cubic parsec in total matter. So let's assume that this is all in machos that are causing microlensing. The Magellanic clouds are at about 50 kiloparsecs from us. And that's all you need to know to be able to measure this, estimate this, this density. And when you do this, you find you end up at about 10 to the minus 7 to 10 to the minus 8. As the probability, as the fraction of the sky that's covered by these disks. So it's a very low probability thing. Right? That's even assuming that you're able to detect all the microlenses, that all the dark matter is in microlensing So, you know, it's a very brave thing that people try to look for this, but they did and they actually found something. So it's quite impressive. The second thing that you can measure is not the amount of microlensing. So this basically tells you at any one moment what fraction of stars is being amplified by at least 34%. Right? That's what this number is. But you can still try to distinguish between the situation where you have lots of little disks or a few big disks. Because the bigger these Einstein disks are, the longer a microlensing event is going to last. The longer it takes before the background star has tracked across the Einstein disk. And so the time scale is called TE, or the Einstein crossing time. And that's the time it takes the lens to cross the size of its own Einstein disk. So it's the size of the Einstein radius divided by the velocity in the plane of the sky. So if your lens is moving at a certain speed v, then it will take a certain time for the lens to cross, for the background star to be no longer covered by this disk, and this time scale tells you what time. And this is going to be different in the two different situations. If you have lots of small disks, then you're going to have more microlensing events, but they're going to be shorter duration. If the disks are larger, then you have fewer events, but they'll have a longer duration. And so by doing the statistics about how this microlensing is divided among a few long events or lots of short events, you can try to find out something about the mass. You can try to estimate basically the average Einstein radius and therefore the average mass of the lenses. So these are the kind of experiments that people have done. And so what I showed you here in this previous slide, this is from the Macho experiment, which was the pioneer in this game in the early 1990s. And they found a few dozen microlensing events by looking at 10 to the 7, 10 to the 8 stars in the Magellanic Clouds. And that turns out to be much lower. In fact, what they found was many fewer events than you would expect if all the halo was covered in Machos. So the conclusion from that is that microlensing is not actually, or microlenses, Machos that cause microlensing are not actually the dominant component of the dark halo. We did a similar experiment this is an example of what they do. So this is the Large Magellanic Cloud, and what they did was night after night, with a camera that could capture a large part of the sky at the same time, just take pictures all around, go round and round and round, and keep this monitoring up for something like 7 years to try to get these light curves for as many possible stars and look for the microlensing events. And so this is the conclusion from that work. Both, I think this is from the Eros collaboration now, but they all more or less agree this is as a function of mass of the deflector. So over a very large range from 10 solar masses, so very massive black holes would be the idea, all the way down to 10 to the minus 7 solar masses, which is pretty light planets. Over this whole range, you would have been able to see microlensing events if they had been common in the galactic halo. And instead what you find is this thick dark line. This is the upper limit that basically says that we know we can rule out dark matter consisting of Machos of all these mass ranges if it contains more than 10, 20, 30% of the halo. So in other words, most of the halo does not consist of Machos over this entire mass range between 10 solar masses and the minus 7 solar masses. So it was a very successful experiment which discovered nothing in a very secure way. So it's actually extremely useful. Of course, they discovered lots of other things. They discovered many variable stars and learned a lot. They discovered lots of planets, which we'll talk about next. But they also showed that the galactic halo does not consist of things which are doing micro. Question?
Yeah, I'm sorry. Can you please go again through the whole thing? The thicker line is what was observed, and are the other lines? So I just don't get it.
So they're combining different experiments here.
Uh-huh.
You can basically do different things. You can either monitor with one field with very short exposures, every half hour, every hour, whatever. And so try to get light curves, try to catch the cases where the light curve is very short and very peaky. Or you can try to monitor a much larger area, but maybe not so often, maybe once a week. And that way you can catch all the things which take a month to go up or down, or 2 months, or 3 months. And so those different time scales, those different event durations, that's what this is, are sensitive to different Einstein radii and therefore to different masses. So the very short duration experiments are sensitive to this range. The very long duration experiments for which you cover a much larger area but not so often are here. And so the different lines here are all different combinations, different strategies, different experiments, which are all combined here in this final analysis. And so each of these individual lines is the upper limit that, for example, in this case, the EROS-1 SMC experiment, that was able to rule out this whole part of parameter space. So it could say, for example, that 60% of the halo consisting of 10 to the minus 6 solar mass objects is ruled out by this experiment. Okay. And so the thick line is the combination of all those different ruling out of different possibilities.
Thank you.
But so the essential thing is that you really have to be able to monitor for or look for events with very different durations, very peaky ones and very long duration ones. So I was involved in an experiment to do the same thing but on Andromeda, on M31. And there you have some advantages and some disadvantages. The main disadvantage is it's a lot harder because all the stars are further away, everything is much fainter. But the advantages are that you can see the entire galaxy of M31 and you can compare different parts of this galaxy. M31, when you look at it from the Earth, is seen very inclined. And so some lines of sight hit the disk very early and some lines of sight hit the disk very late. And so they pass through much more halo of M31 than this one. And so the idea of this experiment was that if you could compare the microlensing rates here to the microlensing rates here, you could immediately see how much of it was due to the halo as opposed to things happening in the bulge or in the disk itself, or in our own galaxy. So it was thought to be a much cleaner experiment, of course. In the end, in astronomy, nothing is ever clean, and so you end up with all kinds of problems because you see lots of dust in these galaxies and goodness knows what. But nonetheless, we did this experiment for a number of years, and we found something like 14 microlensing events of stars in M31, which brighten and fade very quickly and looked exactly like microlensing. If you calculate how many of those events you expect just due to, for example, a disk star at the far end being microlensed by a disk star or a bulge star in front of it, that actually is about 14 or 15. So in fact, we found just the right number of events that you expect just from the known stellar populations and not from any extra dark population of machos in the halo of M31. So also in M31, we can rule out a substantial macho halo as being the main component of the dark matter. So, and this was the work of a very heroic PhD student of mine. So this was done from La Palma on the Canaries with the INT telescope, which is, Rudolf helped me here, this one. And so this is an example of what you have to do then. When you take a picture over the Andromeda galaxy, you don't actually see the individual stars cleanly separated. You see that there's lots of stars here, but for every star that you see, there's another 20 behind it that are too faint, but that are kind of blended with each other. And so you cannot measure the brightnesses of individual stars here. Instead, what you do is you take two images and you subtract them from each other. So here's an image one night, here's an image the second night, and I don't know how good your eyes are, whether you can see any differences. But when you subtract them from each other, then you see that all these little white and black spots, those are stars which were brighter in one image or the other image. And so you basically get rid of all the stars that didn't vary. All this is now just noise, and you end up being able to identify very cleanly the variable stars, even in a galaxy as far away as M31. And so from this, we could then build the light curves, and from this, try to find the ones that look like microlensing. So, okay. So that's microlensing in the traditional classical sense, if you like. That's lensing by a single point mass to try to find out how much mass there is between us and, say, the Magellanic Clouds or also the galactic bulge. What we'll talk about after the break is the funky microlensing, which is what happens when you add second stars, when you go to quasars, when things get much more complicated and much more spectacular. That's at 4 o'clock.
Okay, so there's a piece of information. So as I told some of you earlier, I have the results of the first test with me. If you want to see the test, I will give you them at 4 o'clock. You can keep them. But I want to stress some interesting results regarding the fact that first, half of you are women. So, okay. Now, you know, there is a peak in this block, in this building, regarding the fraction of girls and guys in the audience. Because normally in physical sciences and astronomy, the fraction is lower. The first thing. And I'm commenting this because I want to I just sort the test according to the scores and discovered that the first best scores are from girls, from ladies. So I'm very happy to, yes, it's always like this. Okay, so I'm very happy to tell, for example, that Sibeli gets the higher score, the highest score. Ellie, you also get very good score. Laura Arboleda, Laura. And Natalia, where is Natalia? Natalia Castro, studying. Okay, so this was, yes, incredible. Okay, no, these were really high scores. The rest of the scores, okay, of course, some of them were low, very low. Some of them were in the middle. So I will publish the scores, all the scores, but just with your ID numbers, not to, okay, embarrass some of you. And with Kuhn, we are considering to include a bonus in all the tests according to these problems that cause the largest problems in most of you. For example, I assume okay. For example, we discovered that there were two points in the two questions in the test that produced the largest problems. One was of the identifying the caustic corresponding to this lens, which was really wasn't really intuitive that it was really symmetric, right? Just few, including Sibel and others, identified the symmetric solution. And the other point was one of the true and false questions. Before the last, this question was systematically bad answer, right? So, if you want to comment.
Is this on again? So I was very surprised by this, because this I think is completely obvious. So either this is about my English, or there really is something that is not clear, which should be very clear. But the lensing equation gives you beta as a function of theta. It gives you source position as a function of image position. So if I give you an image position, you can work out the source. There's only one answer. So every image position corresponds to exactly one source. On the same part of the sky, you're never going to see light rays that come from different parts of the source plane. The inverse is not true. This one is not true. Every source can give multiple images, and so you can have different image positions for the same source. But this one here is very much true. Right? And many of you said it was very much false. And the other one was up here. This one here. I think the question was, for this elliptical lens, what is the critical curve and what is the caustic? So I think most of you got it right, that the critical curve would have to be one of these things. The critical curves are smooth, but the caustics can have these spikes in them. Many people said it was this one, that it was elongated. So the critical curve is this one. It's aligned in the same direction as the potential. But this one here many people thought that the caustic would also be expanded, whereas in fact the caustic in this case is very symmetric, it's almost square. And the reason why that can be is that when you map the critical curve back to the source plane to get the caustic, the deflections in this direction are larger than the deflections in this direction, and so these points actually get pushed back further in than these ones to the point where you end up with a caustic that's more or less square. So just because the critical curve is flattened does not mean that the caustic has to be flattened. I don't know why that's why many people gave that answer, but in this case certainly the correct answer is E.
So, taking into account this, just because of the characteristics kind of bias in the test. When test has a few number of questions, it's very easy that the scores get low because of the statistical. So there's a new code for all balance.